going to start. Okay, welcome to Los Angeles Data Platform. Okay, today we have a session by Andy Mallon, and the session is Demystify Data Compression. You can follow us on AOA Data Platform. We are on most social media platforms. And as usual, we are raffling a t-shirt, a custom t-shirt with Los Angeles Data Platform logo on it. And we'll be raffling it at the end of the meeting. With that being said, Andy Mallon with Demystifying Data Compression, it's all yours. Thank you for joining us.
Excellent. Thanks everyone for attending. Let me get my screen shared here. There you go. You should be seeing PowerPoint. If you have, I'll start it now. If you have questions along the way, feel free to ask them in chat. I told Steve he could barge in and interrupt me with questions as we go.
Is there a fan on in the back?
What was that, Kevin? Oh no, my former coworkers are here to taunt me.
Is there a fan on in the back? There's a lot of humming coming from one of your speakers.
There is. Hold on 1 second. Is that better, Kevin? Did that make the humming go away?
Yes.
Yes, that was my mic fan that I had on. Cool. So I'm Andy Mallon. I help people copy and paste code. I recently started as staff database reliability engineer at Stack Overflow. I've been working with SQL Server since 2003. Tech support, DBA, database architecture. My two most important credentials are that I'm lazy and impatient. I like automation. I like queries to go fast. I think that those two qualities are great qualities to have in a DBA as long as they direct their laziness and impatience towards their work rather than by avoiding work. I'm also a Microsoft Data Platform MVP. A couple of pictures of me and my husband and our dogs and my dinosaur, who usually travels with me when I speak at events. His name is Query. He's my favorite dino. My favorite dino. Yes, I said that. If you want to get in touch with me, you can follow me on Twitter at am2. You can email me. You can check out my blog, and all of that stuff is at the bottom of the slides as well. Okay, so let's get into it. We are going to do a quick overview of indexes and heaps. We're going to talk about what data compression is, the different levels of data compression, costs, benefits, do a little bit of a deep dive into the algorithms, and some practical and not so practical examples, which is when we'll get into the demos. We are not covering column store indexes, XML indexes, backup compression, or the compress function. There is a example of the compress function in the GitHub repo where all of my slides live. I think I remembered to include the link to the GitHub repo in the event description when I sent it to Steve. If I didn't, I can paste it in chat before the end of the evening. So in person, I usually ask everyone to raise hands. Since we're on Teams, feel free to unmute or type into the chat if you have an answer to any of these three questions as to whether you've used it, what your experience has been, and if there's something you specifically want to learn today. So if you have any of those questions, either unmute or type them into chat, and I will do my best to address them as we go through the session. So let's start with a quick either review or introduction about how SQL Server stores data. Data is stored on pages. Then those pages get combined into different data structures. It's essentially everything is either a B tree or a heap. Whether it's an indexed view or a clustered index or an unclustered index, it's a B tree. And if there's no clustered index, then it's a heap. B trees look like this. There's a root page at the top, and then you traverse down the bottom. So if you wanted to look up Massachusetts, where I currently am, where I live, you'd start at the top. You'd see that it's greater than ID. You'd go down to the page that points to. You'd see that it's between KY and ME to find Massachusetts. So you'd go to the KY because it's the page that's the first record on the pages. And then you'd find Massachusetts down there in that bottom page. And then there's also some pointers between those pages so that if you want to do a table scan, you can start at Alaska. And when you get to the bottom of that page, you can go directly to the next one. An index seek is when you go straight down. When you look at the read statistics on a query, the number of reads is the number of pages that it read. So the number of these 8K pages, 8 kilobyte pages, when you do a seek to Massachusetts, it's going to go 1, 2, 3 pages, and you're going to get 3 reads. Same goes for Maine. You would have 1, 2, 3 to read down to Maine. And if you looked up both of them, it would take a total of 6 reads to read those 2 states using index seeks. A heap is just the stuff down at the bottom. And in addition to there not being any tree structure, it's also not ordered. So in this example, if you wanted to find Maine, you'd have to read all 6 pages, and you'd find Maine on the last one. If you're looking for Massachusetts, you'd find it on the first page. But because there's no order and there's no constraint to enforce that, you don't know that that's the only one. There could be another entry for Massachusetts later, so you would still read all 6 pages before you found Massachusetts. Or, pardon me, before you finish your query, you'd find Massachusetts on the first one, but then have to read all 6 pages to find out that there's not another one. Okay, that's it for my review on how data is stored. We're going to talk a lot about pages, but we'll come back to that in a little bit. So data compression, it's a different way of storing the data on disk and in memory. The and in memory part is important because when you read or write data from memory, that's when you're going to be decompressing it or compressing it. And that's where you're going to have to apply a little bit more CPU in order to do that. It was introduced in SQL Server 2008 as an Enterprise Edition feature, starting with SQL Server 2016 Service Pack 1. It became available in all editions, which means that every SQL Server version that is currently under mainstream support, you can use this. If you're on 2014 or older that is either out of support or in extended support, then it's going to be Enterprise Edition only. And it's also available in all service tiers of Azure SQL Database, and same with Managed Instance, it's available there. There's 2 types of compression. 2 types of compression. I sometimes will refer to it as types of compression or compression levels. And the one little nuance there is that, not compressed is another level of compression, but it's not a type, so to speak. But I'll basically use them interchangeably as I talk. So I mean the same thing in most cases when I say that. But you can think of these types of compression as scopes. Row compression just looks at the data for that individual row when it decides how it's going to compress it. So it usually, not always, will make the row take fewer bytes. And if the row takes fewer bytes on a fixed size page, then that means you can probably fit more rows per page. Page compression takes the scope of the entire page. First, it applies row compression, then it uses these other algorithms, but essentially all it's doing is it's working to dedupe data that appears on the page twice. That's it. It's really straightforward, but it's only looking at the data that fits on one 8K page. It's not looking across pages to dedupe stuff across multiple pages. It seems kind of obvious once you think about it, but you do have to think about it to realize that. And the syntax is really straightforward. You say with data compression equals and the level, and you can do that anytime you create or rebuild one of these indexes, one of these B trees or tables, even a heap. Alter table, create table, alter table rebuild, alter index rebuild, all of those things are opportunities to change the compression model. To either take an uncompressed index and make it compressed, or to take a compressed index and uncompress it. And if you're using Enterprise Edition, you can do that online, which means it's an online operation to enable or disable index compression. There are a few helpful store procedures that you should know about, and I'll use some of these in my demos later. The first thing I want to say is that SP help index is not helpful at all. It's terrible. I don't think I could recommend anyone using it ever. Instead, use either SP Blitz Index, that's part of the First Responder Kit from Brent Ozar, firstresponderkit.org, or SP SQL Skills Help Index. Both of those are fantastic. I'm going to use the latter one tonight in my demos, but honestly, I probably use SP Blitz Index more day-to-day at work. Oh no, Aaron Bertrand's here too. All my former coworkers are showing up to taunt me. And then the other ones are SP Estimate Compression, Data Compression Savings, and SysDMDB Index Physical Stats. SysDMDB Index Physical Stats is very important to become familiar with. It's an important way to find out if your index compression is being effective. And again, I'm going to use that a lot in my demos later. So if you're going to decide to use it, you have to decide the costs and benefits, because if the pros don't outweigh the cons, then if the pros do not outweigh the cons, then there's no point to do it. So the pros are, of course, compression. If it takes less space on disk, that's great. Less disk is good. And if you copy your production environment back to a QA environment, a development environment, then that space savings is going to multiply with each of those environments that you copy your data back to. More rows per page on disk means fewer physical I/O operations. Again, it seems obvious after you start thinking about it, but it's not obvious to get your brain there all the time. If your rows take up less space on disk, then you go to disk less often. And reading and writing from disk is a lot of times one of the bottlenecks that people run into as slowing down their queries. More rows per page in memory, because it's compressed on disk and in memory, means that you can cache more data in memory. If you have a 256 gig database and you compress it and it's half the size and it's 128 gigs, you can spend less money on memory for your server, or you can maybe have the entire database in memory on your server, and also fewer logical IOs. I'll mention here too that the standard edition memory limit is 128 gigs. After that, your server will not use more memory than that. Your buffer pool is limited there. If you compress your data, you magically get more memory because you can fit more data in memory without adding memory to your server. There is a small CPU overhead with it. The extra algorithms to compress and decompress data does work. Every time you read the data from memory, you always read data from memory. So every time you read that data, you have to decompress it. And every time you write it, you have to compress it. That's going to be a CPU impact. Most people aren't super bound by CPU. Most people have some flexibility to have maybe a single digit increase in CPU, 10% increase in CPU, 5% increase in CPU, 2% increase in CPU. Your actual increase in CPU will vary. So you're going to have to test that. But if you've got a little bit of wiggle room on CPU, you probably don't have to worry about it. And as I mentioned before, if you're on an older version of SQL Server, then this is an expensive edition feature. If you're on 2016 SP1 or newer, then that goes away and you don't have to worry about the version. And now your big con is really going to be this the CPU overhead and thinking about the added CPU cycles it's going to take to read and write this data. Disk is not cheap. Everyone says disk is cheap. Disk is cheap these days. We'll just buy more disk. But we're not running on $200 4 terabyte disks from Staples. Enterprise SAN storage is going to cost you thousands of dollars per usable terabyte. If you do some math on even a modestly sized environment, you're going to be spending a lot of money to buy disks. So then you also have to think about availability groups. Your 10 terabyte database might not just be 10 terabytes. You've got a secondary server. You might have a DR site, copying it to a reporting environment. You've backups take up space. If you compress the data, the backups will be smaller because the database is smaller. Your small 10 terabyte database might have a $500,000 storage requirement for it. So think about that. If you can cut your size of your database in half, that can be a really big benefit, and not just like a nice to have benefit. It can have a tangible dollar amount that you can put on it. And when you can put tangible dollar amounts, like I saved the company $200,000 in storage by implementing this feature, that looks good on your review. That looks good on your resume. That looks good for the company. That's what being a good employee does. You do something that can save the company money and makes use of the technology and tools that you have. This is my diagram of a SAN. If you're not familiar with enterprise storage, storage area network is kind of like playing video game. We are Pac-Man as the DBAs. We're chewing up all of the bits all over the place. And the storage admins are trying to chase us away and get us to use less disk. So this is my diagram of a SAN if you're not familiar with it. So now the fun part, or at least what I think is the fun part. We're going to do a bit of a deep dive into some of these compression algorithms. I firmly believe that if you understand how the compression algorithms work, you'll be able to better decide on your own without needing any fancy tools. Just by understanding how it works, you'll be able to look at data and get a decent idea of whether that data might compress. So this is an uncompressed index. This is the start of the index from one of my favorite cookbooks, the Flour Cookbook by Joanne Chang. I'm not paid to advertise her cookbook, but Kevin's unmuting to say how much he loves flour. Go ahead, Kevin. Go ahead, say it. You want to say you love the cookies, right? We used to walk the flour.
I like the cinnamon buns.
The sticky buns. Yeah, the sticky buns are fantastic. Kevin and I used to walk to flour for a lunch when we worked together. But this is an uncompressed index, right? It's got, this is a non-clustered index on recipe name. You would create index on recipes, parenthesis, name, close parenthesis, done. That's it. Non-clustered indexes also have the clustering key included so that you can find the clustered index with the rest of the data. Those are page numbers in this case. It's pretty easy to read, no problem. Now, if we apply row compression to it, it's going to treat fixed length data types as variable length. It's going to do some stuff around metadata, nulls and zeros to try to optimize how it stores data. But mostly, the first part is the part that you can think about. It treats fixed length data types as variable length, and it smooshes out that stuff to try to fit it into less space. A row compressed index might look more like this. You'll notice that I represented this by squeezing out all of the extra space after the recipe name. And now we fit more stuff on disk. If I go back 2 slides, the uncompressed version only went down to almond roasting. That's as many recipes as it could fit on the page. If I go back up to the row compressed version, now it made it all the way up to bacon and caramelized onion quiche. Delicious for brunch or a snack. But we fit more on the page just by getting rid of the extra space, the blanks. So things like char will be treated as varchar. If you have a big int and you're only storing tiny int values, it won't use the extra space and the difference between storing a tiny int and a big int. Really straightforward. And then I mentioned that page compression uses these 2 more algorithms on top of that. So it's going to do row compression first, and then it's going to use these other 2 algorithms, prefix and dictionary compression, to dedupe the row compressed page. So my super simplified graphic here with being a master of PowerPoint art. First, we take the row data and we row compress that, and then we get rid of the duplicates and get something that is much more concise. Unfortunately, it's not the real life. It's going to be a little bit more complicated. Now we've got pointers at the top, or we've got values at the top and pointers from the bottom pointing back up to the top. So deciphering this is a little bit hard. But we fit more on there. The last entry on this page is now basic brioche. So we can find the bacon and caramelized onion quiche by deduping it. And when we go to look for that, we can see there's bacon and 4-ized onion quiche. So then we can take that 4 and go up and count over to the 4th item at the top. And it's caramel, and I'm using yellow on white, which is really hard to read. But you can see that there's all these spots. Also, I should mention the pages aren't color-coded. SQL Server doesn't store color-coded pages. It's just plain text. But you can see all the spots where there's been a duplicate word that's been replaced with a pointer pointing back up to the top, and that saves space. That is a kind of plain text version of how compression works. And each time we go from uncompressed to row compressed to page compressed, reading these slides has gotten just a little bit harder. It's a little bit harder for you as a human to decipher this. And that's basically the CPU cost. That's going to be the overhead of what SQL Server has to do when you go to read this page from memory. SQL Server has to undo it just like I did, where we take 6 pans and go up to the top and see baking pans. Okay, figured it out. So page compression, do row compression, do prefix compression, dictionary compression. And here's the twist. This is the first time I've mentioned this. If prefix compression and dictionary compression do not save a significant amount of space, fall back and just save a row compressed version. And it does this page by page. So each page in an index, you might have thousands of pages or millions of pages. Some of them may be on a page compressed index. Some of them may be saved as row compressed. Some may be saved as page compressed. Why would SQL Server do that? Go ahead and unmute if anyone has an idea. Why would SQL Server do all this work to compress it and then still save a row compressed version? No takers? So the reason that SQL Server does that is because it's always reading from memory a page compressed version of the page. Exactly, Courtney got it right. So when you read it, I guess Aaron kind of got it right, but he didn't have he was missing Courtney's point. When you read it, when you read that compressed page, if it's page compressed and you're reading it, you have to undo those. So by not writing the page compressed version, by only writing the row compressed version, you didn't get benefit on the space savings. So don't do it. And then when you read it, you only have to undo row compression. You'll save CPU cycles. So that's important. And that's an important thing to check for. That DMF that I mentioned, index physical stats, that tells you the number of compressed pages. And we'll look at that later. And that's how you can tell if page compression is being effective. The other question that I often get is, Andy, you say significant space. How do I tell if it saves significant space? Microsoft doesn't tell us that. That's not documented. In my experience, significant space means you can fit more rows on the page. So if you compress it and you save some space, but not enough to fit more rows on the page, then it will probably fall back to row compression. So I'm going to step through an article to help understand what those two, what that dictionary and prefix compression does. This is the exact same article, or exact same example that's in Books Online. The article is hidden in the crossbar there. When you download the slides, you can click on it. So prefix compression, right? It looks at each column, all of the data on this page for each column, and it wants to find a value for each column where, starting from the left, there's some repetitive value that it can use as the prefix. So left to right, the prefix of all of the words or all of the values. It can be numbers too. Something that is repeated. So in this example, it's going to pick these ones that are highlighted in green, and it's going to write those in the compression information structure at the top of the page. These values get chosen because the start of them are repeated. So the first one, it's 3 A's and a B is repeated on one of those rows. So that prefix can be used to dedupe the start of those words. And then in that third column, A, B, C, D, it's an exact match. So obviously that is a good thing to choose to write in this compression information structure. Then it puts a pointer down at the bottom that says, okay, so I can replace the first 4 letters of this with the first 4 letters of that prefix. So 4B is a partial match. That means that AAAB, I take that, put it back together, and I can piece back the original values. If, for example, in this the second column, this second value, second column, second row, 4 B's, there's no overlap. It's going to put a prefix that says 0 things match from the prefix. And that's where you can start to get overhead where page compression isn't going to work. It's, you know, if it's not finding things, it's actually going to be adding prefixes and not taking anything away. And you could maybe get bigger. Page compression could make the page take up more space, which would not be good. And that would be a good case to not bother saving that, because you're going to do work, make the page bigger. And that's no bueno. All right. So now, I already mentioned this, the overhead here, we've added this compression information structure at the top. We've added these prefixes. Now we go on to do dictionary compression. Now we look not just in the single column, not just up and down for values in the same column that have similar prefixes. Now we go across all of the rows on the page, and we take the prefix compressed, the row compressed and prefix compressed rows, and we look for values that match. These values could be the same anywhere on the page. We write those matching values to the compression information structure at the top of the page. It's clearly late and I am tired. I'm forgetting my words that I just said 2 seconds ago. I wrote those to the top of the page, and I put in a pointer that points there too. We're using zero-based arrays, so we say the 0th, the first indicated by a 0, is that 4b value, and that other value, the second one, indicated by a 1 in a zero-based array, gets written up there second. And this is interesting. This is really interesting, because if we go back and look at the two versions, we deduped as identical values the first and second column in the first row. They're not the same value, but after we applied prefix compression, they were. And we also deduped those 4Bs that were identical in different columns, different rows, but the same value written on the page. We were able to dedupe that too. And in both of those cases, we save space. Now, again, I welcome folks to unmute and just blurt out answers. Did we save space? Did page compression save a significant amount of space on this index? I will pause to take a sip of my drink. I'd usually do a show of hands. And usually when I do a show of hands, I get lots of like, a third of the people are waffling and they're like, well, maybe it did, maybe it didn't. A third of people say I saved space and a third say I didn't. Go ahead.
What was your drink?
Oh, my drink? It's a Artifact cider. Feels like home. So usually like a third of people split pretty evenly as far as think I saved space, think I didn't, and waffling and aren't sure. And then I show this picture because SQL Server doesn't actually store pages like an Excel spreadsheet. I show this picture and ask the question again. Did I save space? And I usually get about the same. Sometimes people change their guesses, but still about the same, a third and a third. And then I do math on you because I'm a nerd. So in this uncompressed version of it, it's filling about a third of the page, and there were 3 rows. So that means that we can fill in this other third with 3 more rows, and this other third with 3 more rows. We'll fit about 9 rows on this page. But in the page compressed version, those are 3 rows, and each dark gray bar means that we can fit 3 more rows. So that's 3, 6, 9, 12, 15 rows. We saved a pretty significant amount of space to go from 9 rows per page to 15 rows per page. That's good. And see, again, this isn't real. This page isn't actually 8K in size, and my example is a little contrived. But we saved a bunch of space. So this is where I switch to some practical or impractical examples. And we'll switch to demos. Before I switch to my demos, I'll again welcome any questions, comments, problems, answers before I jump on to do more. All right. I expected more heckling from Kevin. So I'm going to run through these demos using SQL Notebook in Azure Data Studio. If you're not familiar with Azure Data Studio, I guess I won't go off on a tangent tonight, but I will say Google it. It is it's based off of VS Code, the same way that Management Studio was based off of the full Visual Studio shell. Azure Data Studio is based off of the VS Code shell, so it's got a different look and feel, but kind of a similar idea. ADS does tend to be much better suited for a developer than a DBA, just based off of the tasks that you can complete in it. But the integrated source control is my favorite feature, was my favorite feature. And now notebooks are my favorite feature because when I do sessions like this, I can have code and markdown text integrated together. So I'm going to be running down this notebook for my demos. If you go to GitHub and download download the presentation and the demos, you'll have to install ADS to play through these demos. I think the repo still has the old SQL-based files, but I kind of stopped maintaining them, so they're there just because I haven't deleted them yet. But the scripts won't be exactly the same in those separate text files. So to get started before we came, so that you didn't have to watch databases restore, I took this single backup file and I restored it as AdventureWorks_none, AW row and AW.page. Restored those 3 copies. Excuse me. I created this this view called object size that I'll use a couple of times through my demos, just to show how large things are. And I ran this query. I'll run it again to prove there's nothing on my sleeve. 3 databases, all exactly the same number of rows, same number of pages, everything's the same about them. And now I have this store procedure that I create, rebuild all indexes, where I pass in a compression level, and it does some dynamic SQL to rebuild every index in the database. So now I'm going to do that, create the store procedure, call it 3 times, and we're going to rebuild every single index in the database with no compression, row compression, and page compression. If you have the space to do it, this is a great way to not think and find out if space savings is worth it, because you can just restore 3 copies of the database, compress them differently. If you're not using compression, always rebuild indexes to give them a fresh size when you're doing this comparison, because it might be, you might have page splits, you might have low page fill, all sorts of reasons that your uncompressed index might be larger, and just rebuilding it will compact it a little bit. And you don't want to have a false positive on how much space savings you get because you rebuilt it for row compression, but we're comparing it to an unrebuilt uncompressed index. And now same query using this object size view I created. We can see that overall on the aggregate, as we increase from no compression to row compression to page compression, it got smaller, fewer pages, fewer space on disk. Cool, it works. Except we're going to look a little bit more closely at these 4 tables. So there's 4 tables I picked out to look at. They're not accidents, as you might guess. So I'm going to just use this object size view that I created to look at how big these 4 tables are with the 3 different compression levels. This job candidate table, exactly the same size, did not save any space. So if you compress this table, you're going to burn CPU, save no space, pay cost without getting benefit. Probably doesn't make sense. That one's pretty straightforward. Some of these other ones, though, the person table, you save a little bit of space with row compression and then a good chunk with page compression. Sales order detail, about 3 megs each time you get more aggressive with the compression. And then this V product and description indexed view, you save a bunch of space with row compression, but then not much more with page compression. That is a very long-winded way of saying it depends. Whether or not you'll save space, which is generally the big factor, saving space, which can also save IOs and some get you other benefits, but space savings is the crux of it. Whether you can get that benefit will vary depending on your data types and the actual data itself. So there's not a one-size-fits-all answer where I can say definitely do it. But I will say, and here's where I contradict myself, most of the time, page compression works pretty well on your text data. If you have some repeating data, it works pretty well. Even on identity columns, if you think about identity columns, IDs, if you've got 1 billion widgets in your database, those IDs are in order, and even on the order table, the part ID or something, that part ID is going to be repeated, and you're going to have an index by part ID is going to have the same part multiple times. It's going to be repeated. Page compression probably works. So I often suggest, if you don't have CPU pressure, if you know that you're going to have some sort of data, you start with page compression, then decide that it doesn't work for various reasons. So those results, I just said them aloud. They're written there. You can proofread them later and tell me when I'm wrong. But let's look at one of these in particular. So this is a job candidate table. And for the rest of these demos, I encourage everyone to unmute and shout out answers. And if they don't, I'll just keep calling on Kevin to answer them. He can be my guinea pig. So this one, job candidate, this is the table that did not compress. So we're going to look at this, the information that comes back from this index physical stats function that I mentioned. There are 3 rows that get returned. These are all from the page compressed version. So these are, I'm looking at all indexes on the page compressed version of the table. And we notice that this 3rd row is also for index ID 1. So index ID 1 gets 2 rows when we look at the detailed index physical stats. One is the clustered index. This one here is for lob data. I did not mention this before intentionally. I buried the lead on this. Lob data, things like varchar max, XML data, usually get stored off row on separate pages because they can be 2 gigs, right? Varchar max can be 2 gigs. So if it's stored off row on a separate page, it is out of scope for page compression. Page compression is only going to compress this in-row data. So if you have lob data that is stored off row, that lob data is not going to benefit from your compression. And then if we also scroll over here a little bit, we'll see that on that clustered index, in addition to some of the data being stored on other pages that aren't eligible for compression, we also see that these pages are uncompressed. It wasn't able to compress any of them. And we can tell that by the size. It didn't get any smaller, but we can also tell that from looking at page compression. And if I scroll down a little bit more and we just look at the data, I told you that if you understood the algorithms, you can start to get a feel from looking at the data. Where's the repeating values here? There are none. The repeating value is the XML, which is a lob data type and stored off row. So those big XML documents might have some stuff that repeats, but we can't do anything about that. Here is that index view product and description. I'm going to run the same query I ran before, but for that view. And this is also kind of obvious. Like, oh yeah, like all but one page is compressed. That makes sense. This is the one where we saved a bunch of space. But I want to ask folks, what is that uncompressed page? I didn't tell you, so I don't expect you to know the answer. Does anyone know why there's one uncompressed page? I know Aaron knows. So I'll call on Aaron if no one else answers. Aaron, what's that one uncompressed page? Oh, Aaron's going to ignore me.
I'm not ignoring you. I'm trying to remember.
It's
been a while, man.
So Courtney's onto it. Courtney says a header maybe. The top of the B tree, so the root page and the intermediate pages on the B tree do not get compressed. They're already stored like super efficiently. So the only pages that get compressed are the leaf pages, the ones with the actual index or row data for the clustered index. So every B tree has a root page. You will always, always, always have at least one uncompressed page. If it works perfectly, you get like crazy awesome compression, you'll have one uncompressed page, and that's normal. And for bigger tables where you get intermediate pages, because you need more pages to point down the B tree, you'll get more. So it's normal to have a low number of uncompressed pages. But if all of your pages are uncompressed, that's a problem. I'll just do a quick query here, like a bunch of repeated values. Again, it kind of makes sense that this data would compress. Let's look at this one. This is one of the middle ones, the person table. And here's where I'm going to have some questions for people. Index 1 has 3 rows now. The clustered index has log data, and it's got row overflow data. What's up with that? So this is another case where in SQL Server 2005, SQL Server started to allow you to have a row that's wider than 8 kilobytes. 2000 and older, your row could only be 8K wide because that's how big a page was. So in 2005, they introduced row overflow data where you put your integers at the front, and then you've got a bunch of these wide varchar columns. You've got 20 varchar 1000 columns. Well, all of that other stuff gets shuffled off to the row overflow pages that didn't fit on in row. Guess what? Those 20 varchar 1000 columns, even if they have duplicate data that would be like great for page compression, it won't compress because it's not stored in row. It's stored off the page. The stuff that was stored on the page for the clustered index compressed great. Every page compressed except for that one, the root page. Index 2, same thing, 37 pages all compressed except for that one root page. This fella, 0 compressed pages. Index 3. Why isn't it compressed? I'm going to show the query, but I'm not going to run the query. I'm going to show the index definition. Sorry. I'm going to show the index definition. Index 3. Why isn't this one compressed? Index on row GUID. What is a GUID? Guaranteed unique identifier. It's unique. It's random. I'm going to pay Courtney to come along with me to all of these sessions. She knows all the right answers. If we look at the data, again, just looking at row GUID, select top 50 row GUID. Let me show you the whole query here. Select top 50 row GUID from the table, order by that column, right? Indexes, an index on a column is ordered by that column. So select them, order by them, and look at them. Ain't nothing on here. There's no prefix that's going to be helpful. There's no duplicate values that I can dedupe. That ain't going to compress. And I've got a secret for you. I'm not going to do this demo. There's a whole separate notebook for you to download and take a view through. GUIDs, when you compress them, they get bigger every damn time. Row compression adds overhead, and saves 0 space. And if you have a bunch of GUIDs in an index and you row compress it, it is guaranteed that the GUIDs get bigger and take up more space. So if your index is just on a GUID, don't do it. Also, yet another reason why I hate clustering keys based off of GUIDs, because the clustering key is included on the non-clustered indexes, and then that GUID works against you. Oh, Aaron asked new sequential ID. I didn't even tell him to do that. The demo has new sequential ID. There's a demo on using sequential IDs, and yes, you will save some space on the sequential ID when you page compress it. It will get bigger when you row compress it. It'll get smaller when you page compress it because there's a shared prefix on sequential IDs. Yeah, Aaron, still ick because then a GUID isn't really useful by itself. It's usually a foreign key on other tables, and on those other tables, guess what? They're going to end up being in random orders, and it's still ick because you don't have the sequentialness. If you use GUIDs for your person ID, then on the address table, when you link back to the person, now you're going to have GUIDs in random order, and that small bit of savings where it gets, I think it gets 2 bytes bigger or 4 bytes bigger, 2 bytes bigger, I think. It gets 2 bytes bigger with row compression, and then you save like a little bit with page compression, and maybe you save a couple of percentage space, but then you blow it when you reference it as a foreign key. Here's the other interesting one, sales order detail. So let's look at the index definitions on sales order detail. And I'm gonna scroll over here, make this a little bit bigger so we can see it. I think we can predict, we just learned this lesson, GUIDs won't compress, so we can expect, I think this is index 2, it's ordered by, yeah, index 2. That non-clustered index isn't going to compress. But what do we think about the other ones? The other two probably will. Everything I've said up until this makes you think that IDs will compress nicely. So let's look at the data. So here, I'm going to select the index columns, order by those index columns, hit the run button. We're going to eyeball this data. And I'm going to ask you, will it compress? I think so. That sales order ID is repeated a whole bunch of times. Sales order detail ID isn't, but that sales order ID is. I think it'll compress. And if we go down and look at the other two indexes, here's GUIDs. So I've already wagered that GUIDs aren't going to compress. Here I've got the GUID and the two, the clustered index is these two columns. So we're going to include those two columns too, because they'll be written to the page. Yeah, there's no compression happening here. There's not a prefix that's repeated across them. There's not identical values. Like there's a chance where maybe somewhere you'll find a page with a sales order ID and a sales order detail ID on two different rows that maybe happen to collide, but you're just not going to see it. And this last one here, again, ID values, the index on order ID plus those other columns. Repeated values means that it'll page compress. Now I've got, this says one more thing. It's one more thing in the demo, and then I have a story to tell after that. So maintenance cost, right? The con is, now I've showed you all how to figure out if you're getting space benefits. Now I'm going to talk about the drawbacks and how to decide if those benefits are worth it. Eventually, we have to do index maintenance. You probably don't need to be rebuilding your indexes every week. That's probably wasted space if you're on fast, or wasted effort if you're on fast storage. But eventually you'll probably do index maintenance. Maybe it's going to be to add a column to the index and you're going to have to rebuild it because you're adding a column. Maybe you have low fill where you've had a bunch of page splits and the pages are only half full, so you want to rebuild it to make it not make the pages be not half full. When you do those kinds of things, no compression on this small database took 1.5 seconds, 1,500 milliseconds. Adding row compression made it be just a little bit more time, 2 seconds. And then page compression at 4.5 seconds, so 3 times longer than no compression. Now, in this case, that means that your index builds are going to take longer. If you do have quarterly scheduled index maintenance, that quarterly scheduled index maintenance is going to take longer. If you do it weekly, that weekly maintenance is going to take a good bit longer. But also, depending on how much space you save, it might not be 3 times longer. It might not be longer at all. The first time I did a big compression project was with the database for SAP ERP. We had I think it was 12 or 15 terabyte database. And we just compressed everything, man. We threw page compression on everything. That was SAP's recommendation. So we took their scripts, we vetted them, we ran them. And then the plan was, if we found problems, we would page compress everything, because that's what the vendor told us to do. If we found problems, we'd then roll it back and go back to row compression or no compression. Well, that 15 terabyte database, after we compressed it, was 1/4 of the size. Just because of the nature of that database, and it has lots of repeated values. Because everything was so much smaller, everything was faster on aggregate. So re-index maintenance was faster because there was so much less I/O. So you've got it again, test. So that is one story on weighing these costs. The other story I want to tell is the time that I took down production by compressing an index. So we had this table, and SQL Server was like scanning the table all the time, and we were playing around with different indexing strategies for it. And part of the index, part of the query that was expensive, was like this keyword search thing, and it was a weird table that had keywords in it, but it did wildcard searches. The nature of some of these wildcard searches meant that it scanned a lot. There's some other stuff that was just going to scan because it was, we couldn't change the app, and one of the columns that it searched on was varchar 2000, so it was wider than the index key. It was like problem after problem. So we were messing around with all these different things that we might be able to do to try to make it go faster. Things that we knew would work, or knew that we wouldn't work. We were still testing so that we could take some time off. And I connected to production and ran it on production instead of running it in test. And I compressed every index on the table. And CPU on that server, it was, I think it had 24 cores, modern infrastructure, modern server, 24 cores. And it went from 40% CPU to 95% CPU, and the website went offline. Because this table was scanned so frequently that there were many concurrent table scans happening all at the same time. And they were scanning the table in memory. The table is always in memory. It's cached because it was scanned so frequently. But it was like, I think it was like thousands of times per minute this table got scanned, and it was not necessarily small. So 5 concurrent things started to take a lot longer, and we went from having 5 concurrent index scans to having 50 concurrent index scans because the compression was taking so long to read. And the website went down for about 2 minutes because as soon as I ran it, I realized what I'd done. And I rebuilt it back. But for about 2 minutes, our website was offline. The CTO happened to be walking by and saw the SQL Sentry graph up on the wall and said, "Holy cow, what was that?" Just as the CPU dropped back down to normal. And I was like, "Oh, yeah, sorry, that was me." Yeah, and the website was offline, but it's back now. We're good. So that's the one use case where your workload could be really dependent, right? Like if you have something that is scanning frequently or queries that happen very frequent scans in particular are very costly, but things that do a lot of reads that have to decompress a lot of pages to satisfy a query and run extremely frequently with high concurrency. I think those are all the conditions. That's a scenario for disaster. And that so you don't want to have like if you run a big website on SQL Server, whether it was the auction website that I took offline or something like Stack Overflow, where I work now, those critical path high frequency queries, those are the ones that you want to be mindful of what they're doing when you're testing and do a little bit of load testing to see what the impact's going to be. And then go ahead and roll it out. I also like to start at smaller tables and move up to bigger tables as I do this, if I'm rolling it out widely. But weigh those, it didn't compress, and holy crap, this is gonna get hit a lot, and the CPU cost to constantly be decompressing it is gonna be a lot. It just might not be worth it because you might take down production. That is the end of my prepared slides. I also have all these good things which Aaron asked about. Let's see here. One of these, yes, see here's, it's almost like I knew Aaron was coming, what? But sequential GUIDs. And if I scroll down, oh, I messed this up. I have one more query that I need to paste in here that looks at these sequential GUIDs. The same query I've used 50 other times. I apparently forgot to paste into the bottom of this notebook. Shucks, I can't show the output of that then. Trust me when I say that, yeah, you will save a little bit. So when I do these three columns of sequential GUIDs, so it ends up adding 6 bytes to each row. They get noticeably bigger as you row compress them, and then they get just a little bit smaller when you page compress them. But I'll upload these to GitHub, which I promised everyone the GitHub URL. So let me pull that up, github.com/em2/presentations. And that's it here. Copy, paste. So that is the link that has the PowerPoints. It has the two notebooks here. Aaron, thanks, Aaron. I've got a mechanical keyboard, and Aaron and I have worked together for a few years. And although I left him at Wayfair when I left for Stack Overflow. So he's probably just angry that my angry type. He doesn't get to listen to my angry typing anymore. That GitHub repo that I linked to, that directory that I sent, has the PowerPoint, these two Azure Data Studio notebooks, and then there's a folder called Demo Scripts, which has a slightly older version of these just as plain SQL scripts. So if you don't have ADS, you don't want to deal with it, you can get pretty much all the same thing in plain old .SQL files. Also, if you go up one level to the higher level of the directory, to that presentations folder, you will be able to get to a bunch of my other presentations. I publish them all online. A lot of them are difficult without the context of having heard me give the presentation, but they're all there as well. Okay, questions, comments, problems, answers, something unrelated. Does someone have a Stack Overflow question that they asked and never got an answer to and they want me to go answer it? So I'll just send Aaron, he does that. Aaron, go ahead and unmute, give your ADS rah-rah speech.
That's just it. Embrace ADS. It's that's where they're investing. There's a little bit of investment still in SSMS, but most of the investment's going to be in ADS, and it may never become a complete replacement for SSMS, but that's where they're going. So get on it, and the more and the faster people get onto it, the faster they'll be able to justify investing more into it and making it equivalent or better. And it is better in a lot of ways, to me.
I will say that the source control. So if I save this file here. Oh, I don't have the whole folder opened. Well, I won't do it now. It's all going to be angry at me. But being able to do source control from right here, I don't do Git command line. I never learned it. I never will learn it. I'm a DBA, not a developer. Damn it. Having the GUI for Git built in right here is awesome. It works great for me. And I mentioned these notebooks. I love these notebooks for troubleshooting guides in particular. So I use them for demos, which is one reason I love them. But like a wiki where you have text and then go run this query. And if this query does X, do this other thing. And if it does Y, do this third thing. You can have that all built into your notebook and have a link to take you down to the spot that you need to run or to take you to a different notebook. It's awesome for that kind of troubleshooting guide. Oh yeah, Mike reminds me, ADS is now automatically installed with SSMS 18.8 and above, so you might already have it.
What Mike is probably not telling is that SSMS going forward is going to be relying on ADS, dependent.
Yeah, so there's, I think there's one new feature. I don't remember what it is because it's not one that I use. I think one of the new features is they only did a UI, or they did a UI first in ADS. And they're going to have these cross dependencies where you do a right click, do a thing, and it'll take you to the other tool. So that they're not experimenting with it. It's a little bit more than an experiment, but it's like a V1 of those cross dependencies where you click in SSMS and it opens ADS or vice versa. As we go into the future, we'll have a lot more of that.
Another comment too on the ADS, I have a lot of, well, half of the company did not use Windows. So it was nice to see that it works in Mac OS and Linux as well.
Indeed, yeah. Cross-platform is another big benefit.
And also it's got a nice integration with PowerShell, and we even managed to configure Kerberos authentication, so people start using integrated security right from their Mac OS clients.
Yep. You can have a PowerShell prompt right from here, so you don't have to jump out. So if you're doing
and the excellent presentation. I have a question, somewhat not exactly directly related, but perhaps you could shed some light on that. How do you calculate when a particular role is getting to its 8K limit? It seemed like a trivial request. I mean, we have a application with pretty much every column is and varchar. And once in a while, we get this nasty message that we reach 8K. And so one of the efforts was trying to predict when it's about to happen. And I found out it's not really obvious as far as just collecting, because everything is one chart, so you don't know how much data is actually stored in a row, how much data is stored off row, and
Yes,
it was like I could not answer the question.
So it is a little bit confusing as far as the data that will be stored on row versus not. I would have to go through the documentation to like get a definitive list. They do document. If you look up the, I think the official name for it is wide tables that are greater than 8K, where some stuff can be stored off row. If you look up that documentation, it has the exact list of data types that can be stored off row. But basically, they're variable width data types. Fixed width data types get stored on row, and it's not one-to-one, but that's basically it. So once you have that list of data types, which you could look up, you could query syscolumns, and where the data type ID is that data type, and then sum up the length column. So the length column is exposed in SP help, but the length column is the length in bytes. It's not the length in characters. So like this column here, this nvarchar column is length 16. That means it's varchar 8 because it's 2 bytes. Integers are 4 bytes. Is that right? Integers are 4 bytes? Yeah, integers are 4 bytes. Big ints are 8 bytes. So you'll be able to sum up those, group by table where type is in this list, and sum up the length, and you'll get the length of stuff that must be stored on row.
Yeah, actually, I gave you a simpler version. Everything is varchar max, so that's the key. And I believe there's some there's a certain amount of data still needs to be in row. And I mean, we're talking a couple hundred columns. Some have close to 1,000 columns.
I'm having a hard time understanding how you would predict it, because unless you were always appending data to a column, how would you be able to know in advance that you're about to put an email message body into this column and it's going to overflow the row? Right.
So the goal is, they have all those criteria that customer allows to create for themselves, and the expectation is that they're never going to populate a couple hundred attributes. They're going to populate maybe 50, but we don't know which ones. And so what we're trying to let them know that, hey, you already populated so many that you're close to the 8K limit. And of course, we got to figure out how we're going to communicate with the customer.
So it's kind of one of those scenarios where you have like a customizable product for your customers, and they can do like custom fields type of things in these attributes. And you said there's like 100 of them, so it's like a super wide table. My answer is honestly
more than 100. I mean, I wouldn't be surprised if we have somewhere close to 1,000.
So I would probably not store that as so wide of a table. I would do an EAV, entity attribute value model, where you have, rather than having a column for custom field 1, custom field 2, custom field 3, custom field 4, you have a table that is, the first column is the name of the custom field and the second column is the value. So you'd have a row for custom field 1 and a chunk of text. It's an ugly way to save data.
It's not ugly. Don't call it ugly.
It has. I think everything you're saying is exactly what we all kind of understand. The issue is this is a flattened version that is presented to the customer for their ad hoc querying. So we obviously doing it correctly to begin with, but we have to flatten that so-called data mart, and we're presenting it in the flat version. And this is where we're running into a problem where you got 500-600 columns with nvarchar, most of them never get populated, so we're fine. But a couple customers will get very creative and start adding those attributes. And so the goal is trying to find out when we're approaching this 8K.
I don't think there's an easy answer to it.
One idea might be, because you don't want to be counting non-null columns all the time, and you don't want to be summing data lengths all the time, but you could have an integer that's a computed column that just indicates the number of these varchar max columns that already have values in them, or the sum of the data length, and have that as a computed column. That's not going to add a huge amount of row size, and it only costs you at write time when you're changing that row. So it might be a way that can help you predict. It's not foolproof, and if you jam, in one insert or one update you populate a bunch of these columns, it's not going to prevent that, but it might.
Oh, this is excellent, Aaron. This is excellent. So like a flag for the whole row, or for every. I guess I'm trying to. I guess we could have one for everything, and just get some data.
So you'd have a column that is alter table add foo as, and then you would say coalesce, or you would say if case when custom field 1 is not null, then 1 else 0 plus, and that would be the count of your custom fields that are populated, and then you could have a second one that is some data length custom field 1 plus some plus data length column 2, not some,
wonderful.
sorry, just
wonderful.
data length column 1 plus data length column 2.
Jesus, excellent.
That's not pretty either, and I feel like that's not going to be a full solution, but it might at least allow you to profile the data a little bit.
Excellent idea. Thank you so much.
Any other questions, comments, problems, answers?
It looks like you have an ADS update. Have you thought about updating?
I was definitely not going to update today, because I don't like to update my tools in the last couple of days before a presentation. But also I'm going on vacation tomorrow, so I wasn't updating anything. I've got like Windows updates I need to install too. I'm not installing Windows updates either this week. I can do those on next week when I get back from vacation. I'm gonna stop sharing because you made fun of my pending updates.
I have another quick question, Andy. Did you have any bad experience with write penalty when you use page compression?
There really is no write penalty. There's the CPU cost for writes when it has to do that compression to write the page. But that CPU cost on write is like on an individual on any individual insert is relatively small. The added CPU on insert only becomes a challenge usually on aggregate. So if you have, say you have a log table where you have high-speed inserts going into it, that would probably be something where you'd pay a penalty on it, where the on aggregate, lots of inserts to a log table might be a problem. And if you're doing like huge, large inserts, mostly the only time that you notice that that cost is going to be on like an index build. You're going to notice your index build is slower, and on like a bulk insert, large volume update, you're going to notice it. Backfilling, a new column that you have to go back and backfill and do one of those computation in a loop that runs for a couple of hours. Well, that computation in a loop that runs for a couple of hours to backfill a huge table might run for more than a couple of hours. But overall, it's not very noticeable. The way, and it's because most people do way more reads than they do writes, so you notice it on the reads. What I didn't mention, which this reminded me of, and I should have mentioned, is that you can have different indexes on the table can have different compression levels. So you can have, I kind of mentioned it, like you can have your GUID index that is not compressed, and then you can have other columns that are compressed, other indexes that are compressed. But that applies to partitioning too. So if you have a log table where you have high volume inserts and you've got a volatile most recent portion where the most recent 30 days are really volatile, you can have that be uncompressed. And then the older partitions after your orders are all sent out and everyone's got their stuff and the order's been processed, those you can have be page compressed because that write and update volume stops being a thing, and you're just reading it and you're reading it less frequently. On that like order history or log history, those are excellent candidates to have your newest active partition be uncompressed, and then when it reaches archive age, you add compression to it.
Thank you. Yeah, you answered my second question.
And with like real archive data, something like a cold archive data, that's another good candidate to potentially use column store indexes to get a lot of space savings back. And since he's on the call, I will recommend my friend Aaron's series that he did on, I believe it was on MS SQL tips, but you can also go to his blog, which is sqlblog.org. And you can link to his post that he has published elsewhere on implementing column store on archive data to save a bunch of space.
I'd also recommend Column Score, which is Brent Ozar's site that will take input on your tables and determine if it's worthwhile to consider column store for any given table.
Anything else?
Looks like we ran out of questions. Just in case, if you click on the link, the tiny URL link to participate in our custom t-shirt raffle, please do it so you can be one of the winners of the t-shirt.
Steve, I think we decided we're not shipping overseas, right? Or Canada?
Yes.
That disclaimer. Sorry, guys, if you are overseas or in Canada.
By the way, this is Yelena, one of the co-leaders of Los Angeles Data Platform.
I'm the mostly silent partner. Mostly.
Partner in crime.
Customs does end up being a surprising barrier for something as simple as a t-shirt sometimes.
It's the shipping that killed us. Yeah, the shipping got us. We tried, we really wanted to make an effort and not exclude anybody, and the shipping doubles our cost.
Yeah, Microsoft often has the same similar things because they have trouble with customs and shipping.
Yeah, we ran into an issue.
Well, thanks everyone for having me. It was great to be able to speak in LA from the comfort of my basement home office.
Thank you very much. Yeah, what?
How many people sign up for raffle?
So I have, you're actually gonna make me count, aren't you?
Is it more than one?
9.
Yeah, 9 is good.
9. We're done. Raffle closed. I'm gonna run it.
Your special randomizer.
My special randomizer. Hold on.
While we're waiting for that, who was it that asked about the row overflow?
I think it was Vadim.
Vadim? If you want to email me, I left my email address in the chat. I am really curious about how you actually get into that scenario, because it sounds like a good good blog fodder.
Right. Is this Aaron?
Yep.
Yes.
Yes. I will. Yeah, I'm gonna have to discuss with some of the designers, because I'm basically providing the infrastructure support, but every so often I run into those issues where there's a clearly architect/developer effort. But the gist of that is my understanding is it's a common issue. When you allow people to create their own structures, they tend to go wild with that. I will do that. Thank you.
Are we ready?
Yep.
Kevin, I didn't cheat. You win. Kevin Lou.
Sweet.
See, Kevin, I'm your lucky charm.
I'm actually willing to send him a message with a picture. I work with him now. You're his former, I'm his current coworker. So yeah, this was not, sorry, not fake. It's a very simple randomizer. I just added to a query and just order by new ID. And ta-da.
That is a great use for GUIDs.
Turn off the sound, that's why I can't.
All right, Kevin, I'll send you a link to a form. You get to pick the color, the size, and all that. And give us the address, and we'll send you a t-shirt.
Okay.
Thank you for playing. Was this your first time attending?
I think so.
You should come back.
Thanks, Andy.
Thanks all. Have a good night.
Thank you for attending Los Angeles Data Platform. Thank you.
Thank you all. Bye-bye.
Bye-bye.
Bye.